Hello, everyone, and welcome to our third presentation in the Data Conference. And I have the pleasure now of presenting to you Ibrahim Muzaferija, and he is dialing in today from Sarajevo in Bosnia to talk about cloud computing, anomaly and detection using big data analytics and machine learning. These are all the words that I love hearing as a data scientist, Ibrahim. So I'm really excited about this talk. I will let you give a short introduction of yourself. And so, Ibrahim, over to you to take us through your presentation.
Thank you, Jonas. Hi, everyone. Thank you for joining in. As Jonas said, I'm Ibrahim Muzaferija. I'm a data scientist at Maestro Solutions, and I'm calling in from Bosnia, Sarajevo. So we have a company in Bosnia and in Atlanta, and we have a small data science team that's currently expanding. And this topic is pretty interesting because we have an academic goal and the industry goal that we wanted to achieve with this. So without further ado, let's get started. So for the outline, first I'm going to introduce you to the problem. Then we're going to talk about big data part of the project. That is data collection and analysis and cleaning. Then the interesting part, the machine learning, where I'm going to share with you how we used unsupervised learning to create a labeled data set to discover new patterns, and then use that labeled data set as an input for a supervised model in order to be able to predict anomalies in real time. And then I'm going to share the results and future works with you. Okay, so we have a research objective in which we want to create an efficient anomaly and threat detection mechanism for big data, and a business goal that is industry goal in which we want to increase the security and reliability of enterprise applications in cloud. The main challenges we had that we know from the beginning were big data. We have to store it, we have to process it, we have to analyze it. It's a big challenge. Also, as we want to model user behavior, we know it's complex and it's a bit challenging, especially because the data set is wide and really long. The next challenges were to find the known anomalies and to discover new ones using unsupervised learning. And then in the end, with supervised learning, we want to learn that pattern and devise anomalous behavior detection mechanism. Our research flow was iterative and was based on cross-industry process for data mining. We did a bit alteration in order to adjust it to our case, where we first came with the problem formulation. Once we had a problem, we conducted a literature review in order to see what others did and how, and to stay up to date with the latest trends and technologies in big data, machine learning, and user behavior modeling. Then we have five iterative stages where we understand the business, make up the business goals, draw a project plan, and we continue with data understanding, where we collect the initial data, describe it, explore it, and consult with subject matter expert. And also, I forgot to mention that business understanding in all phases, we are interviewing with subject matter expert because we want to validate some results and so on. So every iteration, we talk with subject matter expert in order to confirm our assumptions and drive the project forward. Data preparation, modeling, evaluation, the usual phases, and at the end, conclusion, where we produce a final report and review the project. So how did we collect that data? The application is B2B oriented, and it serves for the companies and their employees to log in and manage their resources. So the application is hosted on AWS and utilizes a microservice architecture. All the logs produced from the application are then streamed to Elasticsearch, which is a part of ELK stack, which stands for Elasticsearch, Logstash, and Kibana, which is actually a distributed search analytics engine. Elasticsearch helps us visualize and see what's happening on the application. And then the third part is RapidMiner, which is a data science IDE, and which we used to do data preparation, machine learning, text mining, predictive analytics. The RapidMiner is open source and it's used for commercial applications, as well as for research, education, training, rapid prototyping. And RapidMiner supports all steps of machine learning process, including preparation, visualization, validation, and optimization at the end. So once the logs are created, they're streamed to Amazon CloudWatch. The Lambda comes and picks them up to put them in Elasticsearch service. So the first time we saw the data, it looked like this. We had 3 months of data and 5.8 million records. It's important to note that we had 5 available features, attributes, and the data was semi-structured. So even before looking at this data, we had to do business understanding and a bit of data understanding in order to collect this data in the first place. Analysis and cleaning. So first we did a data selection where we understood what is happening, where the data comes from, how it's streamed, do we have anything else there and similar. We had to collect it and explore it, then select the relevant features and take that data to create an initial data set. Next, we did EDA, that stands for Exploratory Data Analysis, in which we did data understanding, a little bit of business understanding as well. We did feature engineering, data cleaning, and we managed to find anomalies. Some anomalies were contextual anomalies, so we discarded them because they were not relevant to our case, while other ones, the point anomalies, were noted for the reference. And as we want to have reference for later while creating a supervised model. Then preparing the data set for machine learning, we had to pre-process it, and there we handled missing values, sorting, selection, downsampling, encoding, normalization, and dimensionality reduction. Actually, all these techniques that we did in pre-processing helped us decrease the complexity of data set in order for unsupervised algorithms to be able to crunch it. So the first time we saw data, it had 5.8 million records, and the data that we took had 500,000. What happened there? We applied filters to remove logs from automated services such as health checks and other application-level services that exclude the user's interactions. And as soon as we did that, we started to notice the weekly patterns in the usage, which is completely normal for the B2B-oriented application. And as we chose the certain features, our initial data set contained 17 attributes. So this is a really important step. Okay, exploratory data analysis. Here we ask questions what and why. We try to understand what's happening and why, draw some questions in conclusions. Generally, EDA is an approach to analyzing data in order to summarize the main characteristics and uncover the underlying structure using statistical and visual methods. EDA is primarily for seeing what the data can tell us beyond the formal modeling or hypothesis testing task. Consultations with subject matter experts are most frequently conducted in EDA phase because it serves as a basis for data understanding. Moreover, EDA serves as a baseline for detecting known anomalies, such as increased errors, strange user behavior, or specific status codes, which will aid in model's performance evaluation. In EDA, we discovered and labeled known anomalies and decrease the complexity of other attributes by engineering them. So the first attribute that we looked at was log status. Here we see that errors are not that frequent, but we still have some peaks, and we noted them for the future reference. Next, we analyze the platform attribute, which reflects where the logs come from, either the backend or browser. And while analyzing, we notice there's an increased backend activity in the 2/3 of data. It was a bit weird, so we continue to analyze more, and we found the same pattern in other features. And then, after consulting with subject matter experts, we realized that those logs belong to the service whose use has ceased and doesn't really have any interactions, doesn't reflect any user interaction. So we discard the data. This is, for example, contextual anomaly, which is not relevant to our case. Even though we are searching for anomalies, we don't want to deal with something that's not related to user behavior. Next, we analyze countries. Understanding where our users came from helps us draw some questions and conclusions as well. We noted that most of our users come from US, then from Bosnia, then other countries. And while drilling down, we find a few countries that only occur a few times, like Malaysia and XX, which stands for unknown country. And while consulting with subject matter experts, he said that those countries don't seem relevant. We can mark them as anomalies, as known anomalies, which we would like our model to detect, the unsupervised model, of course. And status codes. So the status codes are our relic for marking the logs either anomalous or not, either the known anomaly or not. So on the left here, we see that a lot of stuff is happening. We didn't show the OK codes. We only show the 400 client error codes and 500. So we see that errors are quite frequent, but with an ongoing application development, a small fraction of error status code is expected and mainly caused by newly developed application features. We keep all the status codes categories as we want to be able to detect the increased frequency of both client and servers errors as anomalies. Having in mind that this application is being used and currently developed, it really helps us draw lines and understand what's happening in the data. On the right here, we have separated the problematic status codes. So a few 400 and a few 500 status codes, which are anomalous, which are anomalous in any case. So once we were analyzing the status codes, we made a table and with consultations with subject matter expert and decided that, okay, these ones on the right are always anomaly. We mark them because every time they happen, we have some anomaly going on in the system, while other ones on the left can be anomalous only if they have an increased frequency in a certain period of time. All of that is marked and labeled as such. Okay, analyzing the accounts and their distributions, we realized there's a majority of accounts accessing the applications, a majority of the companies, and the two ones are the most frequent. Those two companies are application owners and application development companies. So it's pretty expected that they have the most frequent access. And we noted that for the future reference, because statistically, if they have a huge portion of traffic for themselves, they also can make a bigger amount of anomalies. We also analyze the companies in medium and light users to see when they come to the application, how do they use it, and so on. Continuing to users, analyzing users was a bit tricky. We have a lot of users because each company has dozens of users. And the first thing we did, we tried to extract user domain name from their email address and to analyze that information. Of course, a lot of stuff is a lot of users from one company have the same email address, but although companies have their own domains, there may be cases of other domains accessing company accounts, such as admins, developers, sales, etc. So that's the reason why we did user domain name extraction. And we had a portion of the domains that we didn't know, they were unknown. We also realized that their peak was also in the monthly usage peaks. So we drill down and find that they only occupy a small percentage of the traffic, but still it was really interesting for us to see what's happening there. And drilling down to specific user emails, we realized there's a lot of dummy emails, Hotmail, Gmail, something like that, which are not possible for our application. But then while having consultations with subject matter experts, we realized that those accounts, Hotmail, Gmail, and Outlook, actually belong to quality assurance users. And we marked them as such. And other ones that are still unknown belong to the whitelisted users that are in some trial phase and are using the applications. We didn't remove that data. Both quality assurance engineers and whitelisted trial users are liable for anomaly detection, so we just left it where it is. So the most interesting attribute reflecting the user behavior was research request. It is, aside from being highly diverse, this feature contains key information in modeling application to user and user to application behavior, such as research method used and target application endpoint. Using this information, we can differentiate the request by the method and facilitate unsupervised clustering by extracting the relevant information from the targeted endpoint. And as the resources containing these attributes were highly diverse, we wanted to cut it down, and we cut it down just to the first resource, which reflects which part of the application is being used. So that's the thing that we care for. We don't care which button was pressed on which page. We only care which portion of application, which feature the user was using. And then we extracted both the request method and the resource based and created new attributes. Finally, we did some correlation metrics and weight by correlation, where we wanted to see how the attributes relate to each other. And of course, message and platform were highly related, and message was rated as 0, so we discarded that one. And we could also notice that user domain name has a bit of positive correlation with country, which is also reasonable because a lot of companies operate in specific countries, and most of the users come from that country as well. The other interesting thing that we noticed here was a positive correlation between timestamp and user. This also reflects that certain users have accessing our application as a routine, which is also completely normal because it's a B2B application. Someone comes into work, logs in, it has a routine. So we capture that information here as well. And by weighting the attributes by correlation, we managed to remove some attributes. And we finished with our exploratory data analysis. Now, as you can see, there's a sample of data here. We have decreased number of columns to 12. And I don't remember how many rows we have. Actually, we had 500,000. And from here, we handled missing values. We sorted the data. Sorting the data was an interesting step because data timestamps were down to millisecond, but it wasn't sorted as much because Elasticsearch doesn't care for that level of granularity. But we wanted to have the actions of user represented in sequential manner, and we ordered it by the attribute. We've actually performed the selection as well. We performed downsampling. In the downsampling, we extracted user domain name, which downsamples the user, but we still kept the user because we want to know a specific user what they did. We downsampled resource to its method and base, and we downsampled the user agent because the user agent attribute contained a variety of information about the software acting on user's behalf that's accessing the application, the version, the browsing stuff. We don't care for that much of granularity. We just wanted to see which operating system our user is using. So before downsampling timestamp, which we also did, this is how the dataset looks like. The things that we did next, we downsampled the timestamp because it was down to millisecond, and we don't want to have that level of cardinality in our timestamp attribute. So we first downsampled it to minute. It looked really good. And then we decided to move to an hour. It looked even better. And then we decided to downsample it to actually just day of the week. We have 7 possible values, 6 if you include 0. But if we wanted to capture anomaly that is happening, for example, if a user is accessing the application late at night, then we would stop at hour, but we didn't want to do that. We already saw the pattern, and if some users are accessing the application late at night, it's completely fine. Maybe they want to do something. So we downsampled the timestamp attribute today, which decreased the cardinality by many, many times. And then because all of our attributes were nominal, they were categorical. We didn't have a way to do normalization and dimensionality reduction because they were categories. So the first thing we did was encoded the attributes. We used unique integer coding to encode every category as unique integer, and then we normalized the data in order to be able to compare some attributes. And for the normalization, we used Z transformations. We actually tested a lot of normalization methods empirically. They were all empirically tested, and we chose the Z transformation because it preserves the original data distribution and is less prone to outliers. So after we normalized data, then we finally managed to do dimensionality reduction. It's important to know that while doing dimensionality reduction, we didn't include the attribute anomaly because we kept it throughout the modeling phase just to see to evaluate the model. But we don't want our model to cheat, so we didn't include it in PCA. We only left it aside. So this is how the data set looked like. We kept the variance at 0.9 and we decreased from 11 to 9. Of course, first principal component is accounted for the most of the variety in data set, and it was really interesting to see how the user behavior is actually represented in principal components. We also included, we actually generated the ID attribute, which served as a reference point to know which row is meaning what. Machine learning. So the main challenges we had to face were, of course, scalability, because it still represents a major problem for the clustering algorithms to be solved, and domain knowledge, because number of clustering algorithms require basic domain knowledge to deliver certain input parameters, such as similarity measure, distance scale, number of clusters, etc. But our approach was, once we cleaned the data, once we pre-processed it, we want to utilize unsupervised learning to discover new patterns, to discover new anomalies, because the ones that are known are not that interesting to us. We just noted them for the reference in evaluating the unsupervised model. But we wanted to try different approaches, centroid-based clustering, density, distribution, and hierarchical. In total, we have 11 algorithms that we tried out in order to see how they perform. And once we managed to learn and to discover those patterns, we ended up with label data set with normal and abnormal behavior. It was really interesting discovering all kinds of behavior. And then we used that data set as an input for supervised learning in order to, for supervised learning to learn that pattern and be able to detect on a single instance, on a single data point, whether it's anomalous or not. Because when we are doing unsupervised learning, we are considering a data set as a whole, but we want to be able to do real-time anomaly detection, so we have to learn that pattern using supervised learning. For the centroid-based clustering, we tried out k-means, x-means, and k-madoids. It's a clustering method in which individual clusters are represented by central vectors, and data points are allocated to their corresponding clusters based on their proximity to that center. And during the literature review, we found that centroid-based algorithms are highly effective when used in large data sets, but are sensitive to outliers and initial parameters. Nevertheless, we evaluated this approach as well. Density-based clustering, we have dbScan, local outlier factor, and global homogeneous outlier search. In density-based clustering, it's a method which connects the regions of high data point density into clusters, allowing arbitrarily shaped distributions when condensed areas can be associated. This is really good in our case. And during the literature review, we found that density-based algorithms have troubles working with data sets of variable concentrations and high number of dimensions. By their design, density-based algorithms don't assign outliers, but provide a high distance score, which can be used for detecting outliers at the end. Distribution. We also tried out 3 different algorithms here, and it's a method that treats the data as it's constituted by distributions, such as chi-square or normal. In the case of increased distance from the central distribution, the probability of a point belonging to the distribution cluster is decreased, which actually benefits our case. And important thing to note is that the anomalies that we wanted to discover in the unsupervised learning were both point anomalies, contextual anomalies, and it was a bit hard because we weren't just searching for one kind of anomalies. We wanted to discover all anomalies that are happening in our data. And finally, hierarchical clustering. We tried out 2 methods. And hierarchical clustering is a method that creates a tree-like clusters, as you can see, that are well-fitting for hierarchical data. The main advantage of this approach is a free choice for selection of the number of clusters, as the tree can be cut at any chosen level. The main disadvantage of this method is its complexity, which is quadratic, thus not suitable for dealing with big data, as in our case. But we wanted to try it anyway because we have platforms, we have different parts of application. Maybe we could use that information to devise a cluster tree and use that to detect anomalies or not. And in supervised learning, we have a classification problem. Is it anomaly or not? The main challenges were the data is highly unbalanced. So when we concluded our unsupervised, we have 0.39% of data are anomalous. It's highly unbalanced. And as we want to employ cross-validation, we need the algorithm to be scalable because in cross-validation, multiple models are being created and validated as well. We tried out different types and different kinds of algorithms, functions, trees, neural networks, and memory-based. For the neural networks, we know that we even a priori we knew that it won't be scalable as much, but we want to try it anyway. Maybe we could use a fraction of data and achieve better results, but you'll see in the results page, which comes now. So let's get back a bit and make an overview. What we did first, we did data engineering. We explored the data, we collect it, we select, clean, transform, and pre-process that data. Then we use principal component analysis to reduce the dimensionality of data and lower the complexity. It's important to note that by using principal component analysis, the outliers become even further away from the other data points. So even when we did PCA and plot the results and see how the known anomalies are distributed there, we can see that they are outside the normal behavior patterns, which actually benefits our case. So we even did some anomaly detection in PCA before moving to other phases. In unsupervised learning, we discovered new patterns and clustered the similar data points together across multiple dimensions because we had 9 dimensions that are produced by PCA, as you saw earlier. Then we did supervised learning to learn that multidimensional patterns. And at the end, we cross-compared the multiple created models and verified the results with subject matter expert. The EDA outcomes were our increased understanding of application usage patterns, how the users are behaving, how the application is actually being used, when, how, from where, and etc. We managed to segment the accounts. We didn't keep that information about account segmentation, but we understood that which accounts are using the application most. We can expect maybe increase the number of anomalies from those accounts. We discovered and labeled known anomalies, we created new features, and we cleaned the data set at the end. For the principal component analysis, this is the scatter plot of PCA1, and the color is whether the data point is anomalous or not. But it's a known anomaly, the ones that we managed to communicate out with the subject matter expert, the countries, the status code, and stuff. And we can see that some are even deviating from the general behavior pattern, while others are not, for example, these ones, but while analyzing other principal components, there are anomalies in them. And we also see that we have an increase in known anomalies at the end of the data, which we also noted for the future reference. In unsupervised learning, we tried out 11 different algorithms, and we kind of tweaked the success measurement we want to achieve. So the first thing we considered was clustering efficiency, how the algorithm is able to cluster the data points that are similar to each other and make a huge distance between ones that are not similar to each other. The next thing we considered was data set complexity, because we have 9 columns and 500,000 of rows. It's important for the algorithm to be able to work with that many columns. And the scalability relates to number of rows, how the algorithm is able to work with that large data set. So when analyzing this, we realized that global homogeneous outlier search and random isolation forest are the ones that are more effective. And we decided to combine those approaches because they use different similarity measure. And by combining the unsupervised clustering results of two algorithms, we increase the overall performance of unsupervised learning while maintaining the high scalability and low sensitivity to dataset complexity. As the algorithms are implemented using different distance measuring approaches, random isolation forest is distribution based, and global homogeneous outlier search is density based algorithm. The combination is both partially matching and complementing, which further increases the clustering efficiency we gained. So by analyzing the results of unsupervised learning through the principal component analysis, we see that edge cases in all principal components are captured and marked as such. So the data points that were far from each other are recognized, and that's important for us. We see that some are not that abnormal, but are abnormal in other principal components. For example, here we have a scatter plot of IP addresses. It can be seen that the heavy and medium users account for most anomalies, while in other cases, new and unknown IP addresses are detected as anomalies due to their nature of being new and accessing previously unaccessed combination of resources. Detection of anomalies in IP addresses was one of the important expectations of the unsupervised algorithm, and its accomplishment increases the business value of such model. In supervised learning, we tried out different approaches, and one class support vector machine showed the best. And it's also important to note that our first success measurement was scalability. And how we approach that, we started by using just a fraction of data, random, balanced, unbalanced fractions, in order to try out the algorithms. And the ones that have low scalability, it means that they only work with a small amount of data, even though random forest outputted nice results. It was using a few thousand records. It wasn't using 500,000 as we did. So the results obtained from low scalability algorithms were not as reliable. So we moved on. And of course, SVM was the best one, especially one class SVM. And by using one class SVM, we managed to handle the problem of unbalanced classes. So we just learned the normal behavior, and then we were able to detect abnormal one. It's really interesting that one class support vector machine is also used for the anomaly detection, and we even discovered some new anomalies while using this in supervised learning. It's also important to know that the data set for supervised learning was not altered by the dimensionality reduction techniques, as those techniques require as those techniques consider the data set as a whole. Instead, we use raw values altered to the extent which allows real-time processing, that are attribute selection, numerical transformation, and denormalization. And empirical methods show that it's beneficial for the model performance to have an amount of free space for errors, because the underlying data set is based on unsupervised learning, and we want to complement those patterns, not overfit the model. And even beyond the high measurement scores, we actually saw that the performance of the algorithms was even better. We discovered something new, and the ones that are belonging to development crew that were marked as anomalies in unsupervised learning were considered normal in supervised, because that's something that keeps happening, and it's completely okay with that. So even though we have a weighted mean recall of 90% and the outlier recall of 80%, the actual results are even better. So they complement each other, and we managed to even learn something new while learning the unsupervised pattern with supervised learning. So the output from our SVM was a confidence score. Here we can see the confidence, whether the specific log was anomalous or not. We can see the weekly pattern, and we can see that we have a lot of false positives, which is a bit of a problem. We don't want to have that. But luckily, the confidence score is adjustable, so we can adjust the confidence score and even use the confidence ladder to differentiate between the logs that are just anomaly and the logs that can be considered as threats, like the ones at the bottom. So we have before and after. The first, when the algorithm decided which logs are anomalous or not, we have a lot of false positives because a lot of stuff is happening. But when we just decrease the confidence threshold, when we actually altered it, we managed to get much better informations pulling out, and the pattern is learned. So we can see that the farthest point, this is only the PC1, we can see the farthest points are marked as such, the ones that are really strange are marked as such, and the ones that are in the middle that don't seem to be deviating from the normal behavior pattern of PC1 are actually deviating from the patterns in other principal components, because we have 9 of them. So these are all 9 principal components, and we can see that the weekly patterns are noticeable. The usage patterns are noticeable. We see that some principal components have different kinds of patterns. Some are being broken a bit, some broke up at the end, but it's valid. And the most important thing is that the edge cases are captured. We captured the edge cases, and anomaly detection is actually working. So our contributions were first made to security and reliability of cloud computing. We developed an efficient anomaly detection mechanism for production uses. We contributed with data collection from enterprise application and creation of a real-world user behavior dataset. We made contributions to big data analytics field with complementary methodology for big data mining and data processing. And at the end, with combining the machine learning model and combining those approaches, we managed to capture the complexity of user behavior pattern. We managed to learn that pattern and create an efficient anomaly detection mechanism with a decrease in model aging. Because we didn't consider the anomalous cases, we only tried to learn the normal behavior of our users. And by using that patterns, we were able to detect when something is not normal. Our future works include the implementation of a real-time anomaly detection system. We have a possible improvement in production when we optimize the model in deployment, and when we test it in production, actually. A possible improvement is online training, in which we can automate the process of unsupervised learning, supervised, and updating the model. And this would actually remove the model aging completely. And one other possible improvement is to create, to use ensemble supervised learning, because here we only used SVM as one algorithm, but possible improvements probably could be made by combining the approaches and seeing what works best. Q&A.
Ibrahim, thank you so much for that very, very informative and deeply detailed presentation. I personally have a whole notepad full of questions, but we already have questions from the audience, so we'll go to those. And those of you who have burning questions but haven't asked them yet in the Q&A section, please put them in there. Now, the first question is from Anas, who asks, how long did this project take? Is one. And secondly, did the project go as planned? And thirdly, is there anything you could have done differently?
Okay, it's a great question. The project took 1.5 months. We didn't work on it 8 hours a day. It was a bit less. Did it went as planned? When we started the project, when we formulated the problem, we said we want to make an anomaly detection mechanism to be able to detect in real time, and we want to discover new anomalies. So it went as planned, and actually, we didn't plan to take as much time in data engineering and unsupervised learning, because there we were just spinning in circles until we managed to create an output that was relevant. And is there anything we could done differently? I think that if we have more data, we can play with that as well. But this approach, using unsupervised learning as a baseline and creating a label data set with that, and using the label data set as an input for supervised, made a really good output. And we were actually surprised, even beyond the high success measurements, the algorithm performed really good. Should I read the next question?
Is there anything you would have done differently? Was the last part of that question.
So far, no. We spent a lot of time with that data. We did everything the best we could. Only thing that we would do differently, I cannot think of those things, but we want to implement this to see how it's behaving, and then from that point forward, we can see maybe if some steps we did in the past were bottlenecks, and optimize them as well.
Got it. Okay, so Christoph says and asks a question. So he says, thank you for the talk, is very informative. Given that you use feature reduction and normalization, what is your method of dealing with the outliers you predict? For example, interpolation, generating outlier indices. That's the first question. And second part, and would you consider using these predictions to extend the modeling?
I'm not sure if I understood the question correctly. So given that we used the feature reduction normalization, the method was principal component analysis. And even when using principal component analysis, some of the anomalies were noticed, and we marked them as such because they still represent a valid user behavior. We marked them as such. And even before doing the principal component analysis, we marked some percentage of data set as anomalies, because when we consulted with subject matter experts, we saw that some status codes, some countries are anomalous. We marked them. Output of principal component analysis, when we analyzed those edge cases, we saw that they may be anomalous. We consolidated that with the subject matter expert and marked them as anomalous as well. So we kept the known anomaly attribute throughout the modeling. We didn't include it in the modeling. We don't want to cheat, for our model to cheat. We only use it as a reference to see how many known anomalies could a model cluster, could a model detect. And the other part of the question, dealing with the outliers we predict, that's the way we dealt with the outliers. We noted them, and we use them as a reference while evaluating the unsupervised learning. And in the supervised learning, as we use the one class, we completely remove them from the data set, and we actually use it in validation, so we can see whether those data points were detected as anomalies or not. I hope I answered the question.
Yeah, thank you. I think we have one last question from Christoph that we can sneak in the time allotted. So he says, seeing as the majority are detected in the second half of the distribution, do you think that's due to a bias from the first half of the distribution, or is it something else?
It's interesting question. Thank you, Christoph. Sorry. whether the time is biased. The algorithms we use, they didn't have knowledge whether some action was preferred in February or in March, because when we downsample the data, when we downsample the time step attribute, we downsample the 2 day of the week. So the algorithm only knows if it's Monday, Tuesday, Wednesday, etc. It doesn't know which period of time and which actions came before or after, even though it's ordered in that way. But I don't think it's able to be biased in that way. And while conducting exploratory data analysis, we also noticed that at the end, the last month of data, we had some increases in anomalies, especially because of the development, but not the user behavior. And the results that we obtained show that algorithms is able to capture, for example, if one company is from Sweden and they always log in from Sweden. If they log in from, I don't know, from Africa, it's anomalous, and we algorithm detects that. And if some users do generally they read information, and if they do like bulk delete, we get notified on that, because those data points get marked as anomalous, and we can actually evaluate whether they are threatening or not. But having more data, due to having more data overall, I think the 3 months of data, actually it was a bit less than 3 months, it was 81 days. I think that's a really nice portion. And the data started to being generated 3 months ago. So at that point, we didn't have more than 3 months, but maybe now we could see and try and see how does it perform with larger data sets.
Out of interest, what was your time period?
81 days, so it's actually 3 months. And
what I mean is the dates from October to
from 5th of January to 26th of March 2020.
Okay. Yeah, there could be some user behavior in the last 2 weeks there that could change quite rapidly because of some global pandemic that happened there, for instance. Could be something like that.
Yeah.
Okay. We're at the end of the talk. Ibrahim, thank you so much. Really informative and really a very cool way to deploy a very, very rigorous data science approach to anomaly detection. I loved it. I took a lot away from it. We now have an hour's break, so we'll be back here at minutes to the next hour, depending on in which time zone you're in. So check the Pine Conference Hub for your particular time zone. Christoph and Anas, thank you for questioning and asking questions. Really helpful for us to have this discussion at the end. Enjoy your break, whether it's breakfast, lunch, or dinner. And again, please join me in saying thank you to Ibrahim for taking the time to share with us all his knowledge and the great work that he's done here. And thank you, Ibrahim, and we'll end the session now.
Thank you, Jonas.